All right, so in this example, we're going to probably take a few videos to go into looking at how angular overlap method can be used to predict what structures or geometries for transition metal complexes are the most stable. So the example that we're going to take a deep dive into is looking at two different 5-coordinate systems. And remember, we learned earlier in the course that these two geometries, trigonal bipyramidal and square planar, are pretty similar in energy. But you can have both of these structures existing depending upon what ligands and what metals you have around. All right. So what are the d orbital splittings for, we're going to call it TBP and SP, okay, trigonal bipyramidal or square pyramidal. For each electron configuration, which geometry is preferred? So this part I just got from using the angular overlap method table that we went over in the last video, and I trust that you can do that by yourself and get these same results. Okay, so for all the 5 d orbitals and for the positions 1, 2, 7, 8, and 6 for TBP, and for SP I used positions 1 through 5, right? And so I was able to get this splitting pattern. Okay. And so let's just quickly go over the energy ordering of the splitting pattern before we talk about this more in depth. Well, at the top of the TBP splitting pattern, we have the dz squared orbital with an energy of 11/4 e sigma. Remember, e sigma is a fairly big number as compared to e pi, and we have 11/4 of them, so it's at the top. That's going to be greater than 9/8. Basically, when you're ordering these, look at the amount of e sigma. Ones with more e sigma are going to be higher because e pi doesn't matter as much. Okay, so yeah, you have this 3/2 e pi, but because you have more than 2 e sigma here and just a little more than 1 e sigma, you have more than 1 e sigma total between of the dz square is 1 e sigma, more than 1 e sigma higher than the 9/8 e sigma. So definitely the dz squared is going to be higher in energy than the xy and the x squared minus y squared, which are degenerate. And then you have the 7/2 e pi for xu and yz, those are degenerate. So this doesn't have any e sigma, so it's on the bottom. Now, if you look at this square pyramidal side of things, it's a little bit more complicated, but not bad. At the beginning, at the top, we have dx squared minus y squared, 3 e sigma. Highest e sigma goes at the top. dz squared, 2 e sigma. Okay, 1 e, full e sigma lower, so it's going to be lower. Then you have the xy having an energy of 4 e pi, and the xz and yz being degenerate with the 3 e pi. So these don't have any e sigma, so they're definitely going to be lower. And remember, the value of e sigma can be positive or negative. So if they're positive, the way that I wrote this is correct, right? If it's negative, e pi is negative, and you have a sigma accepting ligand, remember it's a negative value, e pi is a negative value if it's a sigma accepting ligand, and a positive value if it's a sigma donating ligand. So if e pi is negative, 4 e pi will actually be lower in energy than 3 e pi. So there's some complications that can arise here, depending upon whether or not you have a pi accepting or pi donating ligand. We're going to be talking about that extensively now. All right, so what if we have a D0 complex? Well, if we have a D0 complex, we don't have any d electrons. So these are empty, right? These orbitals are empty. And so the energy of TBP is going to be 0, and of square pyramidal is going to be 0. The predicted structure is going to be TBP. Why? Now you default back to sterics and back to VSEPR. TBP is the VSEPR geometry. And you're not really a D complex here, transition metal complex, because you're D0. Well, you're D0, so D electrons are involved. So you're back to S and P orbitals making the difference, which is back to VSEPR, which is TBP. Okay, so TBP for D0. And you can look at these two D0 complexes. This is a titanium 4 complex. So remember that titanium is in group 4. And since this is oxidation state 4, because it's -1 overall and you have 5 ligands, that's going to be D0. Okay, and that's a vanadium 5 complex. So vanadium plus 5 complex. Vanadium is in group 5. So if you remove 5 electrons from neutral to vanadium, you're D0. So D0. What about D1? D1, the energy of the TBP system is going to be 7/2 e pi because you have 1 electron in the 7/2 e pi energy level. And for sp, it's going to be 3 e pi. So these are really close in energy. Okay. If e pi is positive, yes, sp is going to be lower in energy, but only by 0.5 e pi. So it's not a lot. And so if you have a really strong pi donating ligand, i.e. you have a really high positive value of e pi, our prediction is that we will favor square pyramidal. But otherwise, sterics are probably going to dominate and you're going to be TBP. So when you're in a close situation like this, usually it's going to be TBP, unless you have like a really strong type of ligand on one extreme that can shift things the other way. So again, if you have a pi accepting ligand here, remember 7/2 e pi then is actually going to be more stable. It's going to be more negative in energy than 3 e pi. So TBP would definitely be preferred with any sort of normal pi accepting ligand. And so the experiments bear this out. These are both D1 complexes. Here you have just sort of nothing special ligands, and that's TBP. Okay, but here you have an oxide. Oxide is strongly pi donating, so you have a lot of a high positive value of EP. So then that 0.5 e pi difference does make enough. And so it is SP. Go on to 2 electrons, D2. Now the total energy of TBP is 7 e pi, because it's 2 times each of the electrons having 7/2 e pi, and SP is 6 e pi. So again, you're only 1 e pi difference here, so the story is the same. You're going to be TBP most of the time, unless you have a very strong pi donator ligand, which will slightly favor square pyramidal. Okay, and so indeed, this vanadium complex, which is what a vanadium 3 complex, that's D2, that is experimentally TBP. D3. D3 is going to be, well, there's some possibilities here. If you have a doublet, remember, that's going to be spin 1/2, because 2s plus 1, right? So 2 times half plus 1, 2 times 1/2 plus 1 is 2, so we call it a doublet. All right, so the total energy here is going to be now 3 times 7/2, because we have 3 electrons in this energy level. That's equal to 21/2 of e pi. And over here is going to be 9 e pi. That's 3 times 3 e pi. Same sort of story here. We're only, this is what, 10.5 e pi. So we're 1.5 e pi different from one another. That's still not a lot in this sort of context. So if there's nothing extreme in terms of don't have a pi donating ligand, you will prefer the steric geometry, the VSEPR geometry, TBP. Otherwise, it'll be SP. But what's interesting with the D3 case is you can have now multiple spin states, right? So now you can go into a quartet where you have 3 unpaired electrons, okay? And if you're a quartet, now your energy is different, right? Your energy is going to be very high for TBP because you have now this 9/8 e sigma term. So how did I get this? I just added 9/8 e sigma plus 3/2 e pi. There's 1 electron in there, plus 7/2 e pi for this electron, plus 7/2 e pi for this electron. We got this value. And then for here, I did 4 e pi plus 3 e pi plus 3 e pi, getting 10 e pi. So definitely the predicted structure for a quartet D3 transition metal 5-coordinate geometry is going to be square pyramidal, and indeed that's what the experiment bears out. Okay, and so let's go on to D4. We'll go on to D4. D4, you got some different spin states that can happen. What about a singlet? The singlet turns out to be 14 e pi versus 12 e pi, only a 2 e pi difference. Same old story that we saw for D1 and D2. If you have a strongly pi donating ligand, you'll slightly favor a square pyramidal because there is 2 e pi difference here. But otherwise, you're going to go back to the VSEPR geometry of TBP. What about if you have a triplet? Okay, that's with S equals 1, 2 unpaired electrons, 2s plus 1, 2 times 1 plus 1 is 3. So we call it triplet. Well, now again, you have this 9/8 e sigma term. So look, it's definitely going to be square pyramidal because you have this huge e sigma term. Here, square pyramidal, you don't have any of that term. So you're always going to favor square pyramidal no matter what the ligands are if you have a triplet D4 state. And there's even another spin state for D4 that can exist, and that's a pentet, okay? So this is where you have 4 unpaired electrons. And here, it gets a little bit close because you have 9/4 E sigma, the math tells you, plus 10 E pi for TBP versus 2 E sigma plus 10 E pi for SP. And the 10 E pi and 10 E pi wash out, okay? So if you have a pi accepting or a pi donating ligand, doesn't matter. Because who cares if E sigma is positive or negative? That's doing the same thing to both of these structures. But interestingly, so then effectively you're only 1/4 E sigma different here, right? And so that's very interesting. So that's 1/4 sigma E sigma isn't that much, okay, now. And so now it's not going to depend upon the pi donating or pi accepting ability, but actually on the ligand size. If you have a very big ligand, that's going to favor the sterically preferred geometry where you can spread things out, like VSEPR says. So bulkier ligands will favor TBP. But if you have very small ligands, that 1/4 E sigma might make enough difference to make you square pyramidal, okay? And indeed, this is borne out by experiment. When you have kind of small ligands like chloride, okay, that's square pyramidal. But if you have bigger ligands like phosphine, that is trigonal bipyramidal. So I hope you can already see, the power that this angular overlap method has in making really specific predictions about under what conditions certain geometries will exist, depending upon the type of ligands, right, and the spin state of the metals. So in the latter portion of this video, in the companion video, we'll do the D5 through D10 electron configuration.